go ahead, Joe, then, huh? Okay. Um, let me see. Okay, let me share. Let me give you a quick blast through this. I don't mean to interrupt anything, and um, but here and don't laugh again. Um, I just don't have good luck with slides. But basically, what
It's
I
okay.
want to, can you guys hear me okay? Is it coming through okay?
Yeah, yeah, this is good. This is good.
Okay. Basically, what I want to talk about is some file formats that are used. And basically, it'll be BVH, and there's a bunch of CVS. There's a bunch of styles of stuff like this that encode essentially the same kind of information. And the GTLF, which is a big advancement from those, and a little bit about X3D HAnim. Basic skeleton interfaces, uh, fixed frame per second or fixed number of frames. And the idea, kind of abstract, but the idea of video time versus next time. Am I scheduling out a next frame in so many milliseconds, or am I just doing it the next available time that I can make a frame? And so I want to just look at the structural features um, and these possible translations. This is couching the idea of the translation framework and coding choices and possible LTF standardization. Now, what I want to, in my mind, I see characters, I see avatars, I see humanoids. To me, the avatar is basic, the character is extended from that. And then the humanoid, there's an ISO spec of what a digital humanoid is right now. And to my knowledge, it matches well with what the robot folks call humanoid. The idea is to have something that's complex enough to be able to interact and be a simulation for a real character, but also just in web uh, contacts of medical and sports and so on and so forth. And any of these can have an AI. So we had a bunch of early efforts to provide some compute for the mechanical armatures and detailed database interaction and simulation. Um, and so to help with this, I named kind of three categories in this one aspect of the translation framework. There's V1, there's kind of the legendary node, V2, which is improved when you're talking about programming hierarchies, like we see in characters, and V3 augmented with AIs. I don't have much to say about that. But overall, the basic idea is you have a hierarchy of joint objects, parent, child, joint objects, which are really kind of transforms, and that the pose is defined by rotation of these joint objects in the hierarchy. So, for example, the shoulder controls rotation of the upper arm, forearm, and hand. The elbow controls the forearm. And so there's a hierarchy that you can use to set rotations in this hierarchy. So to control pose of the arm with respect to the body, for example, if you're just running the shoulder. And fundamental idea is that one end of the geometry is at a parent, or one is at the parent joint, and at the other end is at a child joint. So when you move the parent, the child moves all the way down the line. So in this thing, I'm thinking V1, legendary, it's BVH and the evolution to GLTF. And there's many other animation intermediates besides BVH and evolution, but the important thing to understand is under the covers, it's the same data or easily converted to same data. And so there's nothing in what we've talked about so far that's hidden. It's all out there. If you're using some certain kind of files, you may have it's all some strange binary that they've encoded to hide it from everybody. And but it under the covers, it's the same thing. So BVH file, I should have some examples here, but I want to make it quick. It tells you about the skeleton hierarchy. It's typically realistic. Uh, it gives the joint center of rotation and how you dimension the skeleton by the root or the first node is relative to 0, 0, 0 in the coordinate system that things embedded in. And then the children joint location is given as an offset that's relative to the parent. So we have each joint node placed relative to its parent. So if you have a hip, then the knee is placed relative to the hip. It's just a style of dimensioning and a basic capability of transforms to be able to build a hierarchy like this. And generally in the DBH, you can have any way you want, but they generally give an Euler angles, and that the way that the data is in these files, find a lot of times, is that they give joint values for translations and rotation, a number of frame and some keyframe time, typically fixed number of frames or a fixed frames per second. So DVH is very general for basic renderers that don't need to know about the skeleton hierarchy. It doesn't need to know about the skeleton hierarchy because it's just a simple thing, and you tell it the translation and rotation of each joint in each frame is given. So they don't have to worry about a skeleton hierarchy at runtime or even in data capture time, and or renders that don't need interpolators. They don't need interpolators because the data for each frame is given. For example, in a video, they have some fixed frame per second and 25 frames maybe, and so give a key time and the data for that frame in every whatever number of seconds it is. So, okay, then we can move to a GLTF, which really standardized some basic avatar nodes and skeleton and animation. In my little simple view here, GLTF gives us a node that's a transform, and it's in the GL coordinate system, and it uses kind of what I call a legendary graphics transform node, which is translation, rotation, and scale. So you can have a hierarchy of nodes here, and the childs are positioned according to the parent translation, rotation, scale. There's some default values for this. Fine. Usually translation is going to be 0, 0, 0. Rotation is going to be 0, 0, 1, 0. Nothing, and scale will be 1. And so we can take advantage of some defaults when we are sending data. It's the same kind of skeleton hierarchy as DBH, and that because it uses the kind of what I call the legendary transform, the root is the first node relative to 0, and then the translation is given relative to the parent. It's the typical way it works. The GLTF also offers this model integration. We can have geometries and direct animations. I mean, we can really build a scene, or at least an avatar character, humanoid, in GLTF, because we got that. And it also adds the interfaces for the deformable mesh. So you can, the point to joint weighted bindings that give us a realistic deformable mesh skin animation. And it includes your samplers, interpolator simple for coordinates, position, color, whatever is live in there, you can animate with interpolators and so forth. Rotations, orientations are unit quaternions rather than Euler angle. So it's what they use at compute time. So that's what you expect. It also has this inverse bind matrix, which in my mind, it just is, you're trying to include a matrix that remembers the joint skin initial pose. You don't need an inverse binding matrix if you don't have skin, if you can just use geometry on nodes. But if you have a skin, then you gotta, it seems to have to reset all to 0 each frame, so you know where you're coming from, so you can do your next absolute setting of the parameter. So it the thing about it is GLTF at this time retains its initial relative skeleton dimensions for the joint center of rotation. Um, so in author time, then you configure the skeleton, you add the details, and then uh, you can have a uh, uh, default or whatever they you put them to. And then the uh, authoring systems will generally add some kind of inverse kinematics to help you drag around parts to make a keyframe. It helps limit joint motions and so forth. And I think this is a real item for possible standardization aimed at standardizing these kind of inverse kinematics to get authoring out into the open a little bit more. Um, so the typical it it this style it documents the joint translation and rotation at key time. Um, and as a matter of fact, in author time, it may that the IK is the only thing it may need to know about the skeleton because it's picking up the translation and rotation. Usually in a hierarchy, the translation of the child is handled by itself. You don't have to tell it what the translation is. You tell it by the parent rotation and location and translation. So it learns from its parent where it is, and then it does its own thing. So it can produce these animation samplers, interpolators, and it gives it a time and a key value for each frame or however you want to do your animation. It uses that inverse spine matrix, and if uh, the default for this inverse spine matrix is an identity matrix, and that turns out to be convenient if you use that capability right. So at the runtime, then uh, the GLTF in its highest order will use the skeleton hierarchy definition and then set the pose and other geometries by the translation and so forth. And they also have jointed uh, weighted joint rotation. Now, conclusion of that is that the skeleton hierarchy is maybe not necessary in runtime in some situations, and it's a whole bunch of data because you're given in a fixed frame or a fixed frame per second, you're sending a whole bunch of data and so forth. So, and it the both of the GLTF, I think, gives you this facility of setting up fixed frames or fixed number of frames in there. And but once again, okay, now we come to
Joe,
V2, which
there's
is
one hand up if
yes,
you want to take that.
Joyce. Oh, okay. How
Hi,
about
hi. Yeah,
okay?
sorry.
Go
I
ahead.
can let I can let you continue if you want. I just wanted to just make one comment is that at runtime, especially if you don't have to be in VR, but for person player, the one thing that you're going to have to do if you've got a full body avatar is calibration of the avatar skeleton to your
Yeah,
height. So this just FYI at this point. That's all. I just wanted to make that comment.
good. For V2 here, in this model that I'm using, we enhance the animation of hierarchy by adding a movable center of rotation relative to translation. Now, there's another feature that's real nice when you have this is that you can move your center of rotation around your avatar. For example, if you're having an avatar where the center of gravity changes because of its pose, you can move that node. You can move for example, you can move your root node to that new center of gravity if you're doing computations that way. So it just adds a bunch of things when you add this. It's relative to the translation. And so when the translation of the joint changes, well, the relative center of rotation that you're specifying changes. If you don't have a center here, then the center is at the translation. So if the default center is 0, 0, 0, then it's the same as the translation. So it just allows you to move the center of rotation away from your translation value. And so in author time, then we set the joint at here, and then we set the center of rotation relative to the correct end of the bone on, so that the thing rotates as expected. The idea here is that the translation, rotation, and scale remain at a default value, and the center tells it where to rotate. And if you put that joint in the correct position in the hierarchy, then it just happens magically, thanks to the magic of 3D graphics. It just happens to work right. So the dimensions of the skeleton now are the joint center of rotation value are measured absolute relative to 0, 0. So instead of positioning a shoulder relative to the hierarchy of the joints that are under it, I can just draw that center of rotation. I can measure where my shoulder is, and I can put that center of rotation at the shoulder. In the old days, the beginning of humanoid modeling, there's a giant projects about measuring people, and they all just happen to measure people at 0, 0, 0s in the middle, between the feet. And a lot of those measurements were taken laying down, but anyway, it just became a standardized way of defining measurements of this human in this database, is that they measure it relative to 0, 0, not relative to another feature. So the skeleton joints in humanoid space, or whatever container that the character is in, and then the skeleton features are in joint space. And all the
Joe,
joint
just a minute,
centers.
Joe.
Okay.
There's again a hand up. Let's try to take that as we go.
Okay.
Just more of a time check, Joe.
Okay, 1 minute. Okay. So absolute and relative. The way we deal with it in, I mentioned a form X3D, is that the ISO spec for the humanoid and this sort of using center we cover in part 1 of it. And then when we're dealing with things that are built with relative dimensioning, then we deal with that in part 2 of the HAnim specification. And so the main idea is that when you animate the thing, you can use a Unity IB inverse spine matrix. You got to take care of the center, but okay, so that's kind of enough. There's a way of modeling this using 2 transforms, and then finally there's a OUSD interface called pivot. It's not too well defined, but I want to try to get that into a specification so we can handle these 2 different ways of dimensioning a character. So thank you. Any more on
Thanks,
that?
Joe.
So that's kind of the style of what I wanted to bring forward. Thank you.
Okay. And yeah, just a sort of like a newbie question. So what's the intention? Where do you want to go with that? The topics that you presented.
Well, when we want to transform the translation framework, where we take an avatar and move it from one to some rule, we want to have a good path to deal with these avatars that are dimensioned relative, where the dimensions are relative to convert it to a avatar back and forth. So
Oh, okay, I
it's
see.
just a consideration in the conversion from one style of mentioning to another. Just a
Okay,
consideration, that's all.
I see.
Underneath
So
that,
yeah,
I want to have a GLTF that has the pivot or equivalent in there. So
okay.
reaching,
Yeah,
very reaching here. Thank you.
yeah.